I would lead anything to do with me with a disclaimer. It's like, this may suck. Actually, it probably will suck. It's probably going to get off track and out of order, and there may be some random male nudity. You know, just.
We need to sign a consent form first.
Hey, it's all on camera. So.
You're here by your own volition, so there's no. Yeah, we got that on record. Like, you came on your own. We didn't force you. All right. So today we're going to talk about inputs and outputs pertaining to automation controllers, unit controllers, basically any kind of controller. We'll start with inputs, just to make sure everybody knows what we're talking about. An input is a field device to the controller. An output would be the other way, just to make sure we are all on the same page. Do you understand? Do you understand? Do you understand? Do you understand? You? I don't, so I'm just checking with y'all. So field device to controller would be an input. To the controller. All right. So there are two types of inputs we can have. There are binary. Spell that right? Yeah, it's right. It's binary. Binary is the simplest kind. It is either on or off. A 1 or a 0. Very simple. Not a whole lot to it. That's binary, okay? 1 or 0. That is binary. Right. I'm getting to that. So, examples would be a airflow switch, like an air proving switch on a fan or a heater. It could be a CT on a pump, a motor, a compressor. CTs monitor current, by the way, just in case anybody knows. Although CTs, we're not going to go with that one. Screw that. It's not CTs. Right, exactly. That's why I'm saying I'm not going to go. I won't use a CT as an example, because you could have two kinds of CTs. You could have a current switch or a current transducer. So to me, CT is not the right word to use. We'd use like a current switch. So let's do like a CS.
But on this, correct me if I'm wrong, even on like a schematic, so say we went to just a box that had a factory CT on it, but it was a binary type.
Yeah.
Wouldn't it? They still represent that as a CT.
Yeah, they're all represented as a CT, but it's not really a transducer at that point, right? A transducer is going to put out an analog output. To me, that's what I consider a transducer. But I guess it is still. I guess the load going through it is creating a magnetic field, which is causing it to close the contact, and that's a transducer, whatever. But we'll call it a current switch, just for keeping things binary and analog. It could also be like if you have a high pressure switch, if we're monitoring like a second high pressure switch on a compressor for a safety in the controller. Those, huh?
High static.
Yep, be a high static. It could be, heck, it could be a low static. Just depends on how you program stuff. Basically, anything that has a set of contacts and we're monitoring an on-off value, a 1 or a 0, a yes or no, true, false, all falls under binary. Some controllers require, sorry, that's me really loud on the camera. I forgot there's a mic here. Some controllers require what we call a wet contact. They require voltage. So even though it's a binary, it doesn't just monitor the resistance. It actually needs to see voltage present. Some of the, I'm trying to think what brand those were. There's some I/O modules for our tritium devices that require a 15 volt DC on the input. So if you just put a dry set of contacts with no voltage present, like an actual, just an airflow switch with a reed switch on it, it won't do anything. You have to put voltage through that reed switch to come back into the controller for it to recognize that it has a contact closure. So, what do you mean? I don't know what it's going to look like on a schematic. I can draw what I would represent it as. Like, so like, all right, so say we have, here's our airflow switch. It has 3 contacts. Common, and we got, normally, hey, I'm gonna make this a little bigger so we can actually see it, because I forgot I'm showing a camera. All right, so we got 1, 2, 3. Common, normally open, normally closed. And these are our screw terminals. So you would need a so you have a transformer. Typically, I would take the common side, run it through your switch. The switch closes, completing a loop, sends back to the input, and then the other side of your input is wired back to the transformer. So you're sending a 15 volt signal, basically. So even though it's binary, they're not, on the controller, it's technically not a contact, it's actually measuring voltage. So it would be a universal input at that point. So it's an input that can be configured to read voltage. So it's not actually just saying, hey, I've got a contact, I don't have a contact. Basically, that input does not have a source of voltage to push through this set of contacts to be able to recognize that a closure has been made. So,
how much do we see that style versus?
Rarely. We rarely use them.
And the Distech and Honeywell don't have that.
Don't need them. Nope. So both Distech and Honeywell, you can set them up with a dry contact. No need. Johnson Controls can be a dry contact. Most stuff will work dry contact. Even on, so like Honeywell and Distech, I'll just stick to those because that's what we do the majority of, actually have universal inputs, and those universal inputs can be configured as a dry, or you can use them for monitoring a thermistor, a transducer with like a 0 to 10 or 2 to 10 or 4 to 20, or they can monitor just a contact closure because they can source their own voltage from the controller basically to send something out and bring back. They don't need something from somewhere else to relativize, to recognize that. But like I said, the majority of it, we don't do that. It's just a dry contact. So you can just literally take a wire. So it would be, all this goes away, and then you just have straight to your field device. So you don't need anything in between. You can literally just run a 2 conductor straight from the field device straight to the controller. So we won't spend a ton of time on that just because it doesn't super pertain to us. The next up, so basically binary is, like I said, on or off. Anything that would be on or off is going to be a binary because it's on or off. All right. Next up is going to be a modulating input. The best way to describe modulating would be scaled. So anything that can be scaled, a resistance, a pressure, a output, like a 0 to 100% value type situation. Damper actuator, a chill water valve, a hot water valve, a pressure transducer on a line set, monitoring high pressure, low pressure, static pressure in a ductwork, pretty much anything that is scaled. So if you've got like a thermistor can be, let's say the range of the thermistor is -20 to +200 Fahrenheit, and then you know that resistance scale goes from, let's just use round numbers, 1,000 ohms to 5,000 ohms. And so it would be like, if we do -20 and then 200, and then this is not correct on this, but let's just go 1,000 ohms, and this would be 10,000 ohms. So it's scaled. So -20 equals 10,000, 200 equals 10,000, and you have a relationship between the two. So those can be resistance, they can be voltage, and they can also be amperage. So we have resistance, voltage, which voltage is going to be DC, like a 0 to 10 or a 0 to 5, something in that range. And then amperage is going to be your milliamp signal, a 0 to 20 or a 4 to 20 input. Resistance are going to be, at least in the HVAC field, are typically your temp sensors, thermistors. Oh, was the door locked? Oh. Jeez, Casey. Resistance inputs are typically going to be temperature sensors. There are a couple different kinds of temp sensors depending on what brand you're working with. There's 1K nickel. There is 10K type 2, 10K type 3, 20K. Different companies use different scales. This is typically JCI. These two would be Distech. Lots of companies use 10K. Distech, KMC, Andover, Novar. What else is out there that uses it? There's a lot. It's probably the most widely used resistance scale is going to be 10K type 2 or 3. 20K is pretty specific to Honeywell. There are a few others that can use it. And then a lot of controllers can be scaled, custom scaled. So if you've got an input, you can actually write, like I could write a program that'll have the 1K nickel in a Honeywell controller. It just has to be custom written. They don't always have a drag and drop utility to do it.
What's the difference between type 2 and type 3?
Don't get me lying. I think it's the range. Yeah. So like typically on a 10K, it's 77 degrees Fahrenheit at 10K. But I think they're both pretty close to that. And then they're like, it's basically the curve, right? That bell curve that they have is different. Then there's even like a 10K type 3, something else on the end of it that has like a reversed curve or something to that nature. I don't remember. There's typically we really only use those 3 and we stick them to those 3 brands. So 1K nickel for Johnson, 10K type 3 for Distech, and a 20K for Honeywell. That's their default sensors. So we don't have to scale anything, we don't have to create anything, it's just a drop in there and rock and roll. The charts are really easy to find. Just the best one I find that's the easiest to get to is on a company site called BAPI. BAPI's a sensor manufacturer. If you Google 10K type 3 thermistor chart, you'll probably end up with BAPI as your first choice on Google. They're real easy to read. It looks like just an Excel spreadsheet chart with a couple columns and a bunch of rows, and they'll list out a temperature and an ohm, a temperature and an ohm, and you just correlate whatever your temperature you're reading. Like say if you put your meter in the water and you get a reading, and then you take your meter and put it on this thermistor and you get a reading for ohms, and match the 2 up and see if it's right or wrong. And if it's bad, throw it away, replace it. So, but we can.
What range of tolerance would you give?
Depends on the sensor. So each sensor has their own range of tolerance. Most of them are 3%, some are 5%. It just depends. You would find that out by looking up that part number. So,
Like a rule of thumb, like in service, we use most of our sensors. We get like a 2-degree rule of thumb.
yeah,
If we're within 2 degrees,
yeah.
plus or minus.
I try to say around 3, because think about it. If I've got, most sensors are 3%. That's what safe rule of thumb is, just say a 3%. So if you've got 0 to 100 degrees, right? A 3% span is 3 degrees of that, right? So if you're reading 71 in a space, sorry, that's a 0. I'm thinking ahead of myself. And then your sensor's reading 70, I wouldn't even bother calibrating that. There's no point. You have a 3% accuracy on a sensor, you're 1% off. There's no reason to even calibrate it. You will chase yourself. If you start calibrating this to match that, as the temperature goes up, that's going to change, and then you're right back to having to calibrate it again. And you're going to end up just back and forth, back and forth, back and forth. And we struggle with that with some building engineers, because they'll walk around with their little thermometer stick and set it on a thermostat, and it says 72, and the system reads 74. And they're like, well, the sensor's bad. Like, no, it's 3%. It's within the range. We can calibrate it, but come summer, when it gets 76 in here, it may be 2 degrees off the other way. I can't guarantee it. So the other thing is, some jobs require us to calibrate based on the wire length that's being ran, but we don't have to do that because as long as we use the specified wire with the resistance for that controller, it's already factored in. So like Honeywell is, as long as we use the correct impedance wire, which is impedance is basically resistance per foot, up to 300 feet, I don't have to put any calibration. It's pre-done in the controller. It knows, it's got that factored in. So that input is already set up like that to where it knows that it can be. And I think that's kind of why they come up with the 3% variance too, is to account for that. So, I don't know.
You have to put in a correcting factor if you were to say run.
Well, we would just calibrate it at that point, right? There's not like a correcting factor. They give me an offset in the controller. Like when I go to that input, I can offset it based on whatever facet it is. If it's temperature, I can offset it by so many degrees. If it's pressure, I can offset it by so many PSI. Some of them you can calibrate the actual resistance, but most of them don't show us an actual resistance on the input. They show us a faceted value, right? So we don't read the true input on the terminals in the logic. We're reading whatever our calculated value is. So it takes the resistance, the block that I'm looking at already does all the calculation in it and spits me out a degree number, like 72, 73, whatever. So it may be reading, 12,000 ohms technically at the sensor, but the logic block that's dropped in there that holds all that pre-calculates it, and I never see the actual ohm reading. So I can configure them that way, but then I'm building the whole block myself, and it takes a whole lot more time. So we use the GUIs for a reason. All right. So then there's voltage inputs, which a voltage input can literally be anything. Same thing with the amperage. We'll just classify these together. They can literally be anything because it's scalable. I can take anything that's a voltage, 0 to 10. So it could be 0 to 10, 0 to 5, 2 to 10. And then a lot of these, so like Honeywell and Distech and JCI, I can make this a 3 to 5 volts. I mean, I can configure it any way I need to based on that field device.
You can troubleshoot that live.
Yes, yeah.
Without having to so with the ohm value, you have to disconnect the sensor and test it.
Correct.
This
I can actually land it on the terminals and read a voltage there. Amperage, not so much, because to read milliamps, you have to be in line on most meters, unless you have a really, really expensive Fluke milliamp clamp meter that you can clamp it on the little bitty wire and read milliamps. Yeah, good luck. They're like $2,000. You got to disconnect it and put it in line with your meter. So you do have to unwire for amperage, but we'll get into all that. I'm going to do like a troubleshooting section towards the end. But yes, so these can literally be scaled. Your amp stuff will not be. It's either a 0 to 20 or a 4 to 20, more than likely. Everything I've ever done that's had amperage inputs are your set. The only thing you can scale is your value for that window. So I could take, let's say I have a temperature transducer instead of a temperature thermistor, right? A thermistor is a resistive input. A transducer is going to take, there's more than likely a thermistor on the actual field device, but it will take that and convert it to a 0 to 10 signal inside of the sensor itself. So if that sensor puts out a 0 to 10 signal, I can then, in the software, scale it to whatever that sensor is. So let's say that sensor from Honeywell is a 0 to 10 voltage, and that tells me it's, let's just go crazy. Let's go 0 to 300 degrees. I have to, in the software, figure that 0 to 10 equals 0 to 300, and it will scale that input to where when it gets 10 volts, it knows it's 300 degrees. When it gets 0 volts, it knows it's 0 degrees. So, and I'm using round numbers here. Nothing is ever that simple. It's always some weird values. It's never a nice round number. So it just never is. But I can do that with anything. I can do that with pressures. I can do that with, I don't know, temperatures. I can do it with a float sensor in a well. I can do it with, whatever you can. If you got a sensor that'll put out a 0 to 10, I can scale it in an input and monitor any value at that point. Because once it's broke down to just a 0 to 10, all I need is a way to configure that in the system. I can do electrical meters. You know, it can tell me, oh, hey, 5 volts is drawing 500 kW. I can do that in a controller because it's scalable, right? It's so. Yeah, 100%. Yeah, you know, 5 volts DC equals 24 gallons per minute. It's just in how you, it's just a correlation, right? You're taking whatever that scale of voltage is equals whatever your, we call them facets or values are. Literally anything. So it's kind of cool. That's the best kind of inputs. You can do whatever you want with them. 4 to 20 is the same way. It can be anything. Like I said, typically in all the controllers we deal with, we can't scale the 4 to 20 or the 0 to 20 input. We can scale the value it reads, but they're either going to be 4 to 20 or 0 to 20. Most stuff we deal with is 4 to 20 as well, not 0 to 20. But the thing about amperage is some of them are DC signals and some of them are AC signals. So they get kind of convoluted. A lot of them require their own power source. We don't do a ton of 4 to 20 anymore in the HVAC world. PLC still does a ton of it, but we don't really do it. Most everything's converted to 0 to 10 just because it's simpler. So, all right, so that's something it could be. It could be like a positioner on a valve. Like Belimos, give me a feedback signal. 2 to 10 volts coming back from the valve to tell me how far open it physically is. That's the other thing that could be for a binary when we were talking about earlier, an in switch on an actuator or a damper can be a binary input as well. So something else to think about. I forgot about that. I should look at my notes more often. All right, well, any questions on inputs? All right, so outputs. Same deal, binary and modulating. These are going to be things, anything that you're turning on, so on or off values. Let's say like a motor starter, a 2-position actuator, relays of any sort and kind. What else could be a binary? Yeah, basically anything that's going to take like a 24 volt signal or 120 volt signal, whatever it may be that you're doing. Yeah, on or off. Start it off, shut it down, that kind of stuff. Very simple, nothing to it really. There are a couple different kinds of binary outputs. I'm going to focus on 2 of them because we don't really mess with this third one, at least not in our world. I'll touch on them at the end just so that y'all know about them. But the are a relay, which is a mechanical. I have to, man. Mechanical contact. So just like a contactor and an air handler, right? It's an actual mechanical contact closing. So inside the controller, it's going to send a signal to these little bitty tiny square blocks on the control board with basically a micro relay in it. And it's going to close a set of contacts and take whatever's coming in and pass it back out. So relays have a couple benefits. They are better at holding a load, and they isolate the controller from any like errant voltage. So if we have, say you're using it to start a heater, right? And it has a big contactor on it, and that contactor burns up and sends voltage back down the control wire to the controller. A relay will isolate that controller and prevent the controller from burning up. Our other type of binary output is called a Triac. That Triac is a solid state relay. It will burn the controller up if it gets voltage on it. End of story. It will toast it. So you go from having a $15, $20 contactor fail on you to having a $400 controller. So, which when Honeywell first came out with their controllers, they have Triacs and they were rating them at 1.3 amps, which is great. But then people started putting them on heaters without isolation relays, and the contactors would fail, or they would start to chatter and they'd increase the amp load and would burn up all the Triacs in these controllers after like 2 or 3 years. So Honeywell puts out a memo like, hey, no, we definitely, and if you read their documentation, it said to use an isolation relay. Called it out, but nobody ever did, because if you've got 3 outputs on a controller and you got to add 3 more relays, that's another $100. So nobody want to spend the extra $100 for a fan power box to put isolation relays. Now we pretty much, that's all we do. We will not do a job without relays because of that problem.
Are there companies out there right now that still practice non-ISOs?
By companies that practice, do you mean a manufacturer recommending to not use an isolator, or a company installing said equipment not using an isolator?
Yeah, like a local install company, not to name names, but just are there any locally that?
We've done it as recently as yesterday because the customer doesn't want to pay for the relays. I can't make them pay for the relays.
Right.
We give them the caveat, we put it in writing saying that we're not going to warranty it for that reason, and we'll move on. I don't recommend it. Flat out. That's why we put it in our warranty letter. If we sell a job without relays because they want to cost, value engineer it, whatever it may be, however you want to call it, we put it in our warranty letter that we're not going to warranty the outputs. So, because of that exact reason. So, because people do. Like I said, you're talking about $100 per controller to add 3 relays. And you're already talking about a $400 controller. Now you're talking about $500 instead of $400 for the exact same function, right? Because it's going to function, it'll work, but will it last?
So that would still be cheaper than letting it go ahead and burn out. Now you got a service call. Now you're going to be way up more than
Exactly. But that, yeah. Yeah. Hey, I'm with you. You would think that like people can rationalize that, but sometimes they don't have the budget. There's nothing they can do about it. I mean, property managers and engineers get bent over a barrel just as hard as we do. They're at the owner's behest. I mean, if the budget's not there, and you're talking, you've got 300 controllers in a building, and you're at an extra $100 per controller, that could make or break the job. I mean, or when we get into bidding wars is when it really sucks. Like because we've done it when we have to. There are other companies that do it just for the heck of it to win a job and won't put them in there and did not even tell a customer about that. And then we're like, well, hey, what's apples to apples here? No, they don't have isolation relays in all these controllers. They didn't put a controller with relays in it. They put a controller with Triacs, and we'll explain the whole situation. And then we may win a job because of that. Because we're like, hey, look, we're saving you service calls in the future. And this is not to say isolation relays are the end-all be-all, because they can still blow up too. But it is a $15 relay ice cube versus a $400 controller. I'd rather take the risk as popping a $15 relay cube. So, because usually the bases make it. It's the cubes that don't, because they have these little bitty like 22 gauge wires inside of them that just can't hold any amperage. They heat up, they burn up, then it arcs, and whole thing's toast. If Holden would let me use a projector, I could show y'all some really cool pictures of some crispy ass stuff. But
You are off the screen.
am I in it now? Ah. Hey man, I'm like Oz. I'm just in the background.
Are the HVAC controllers Triacs?
Which one?
PCB 1630, 1620?
1620?
I don't know what labels over it.
Okay. Some of them are, some are not. You have to look at the actual, and then some controllers have a mixture. So like an ECB 203 has triacs and relays on it. The first 6 outputs are relays. The other 3 are called universal outputs. They're UOs. Those are triacs. Or they're not triacs. They are actually the other kind we weren't going to get into very much, but they're a transistor. So a little bit different in the way it works. It's a different kind of electrical component versus a triac. A little over my head with how to explain those. Not an electronics guy.
They still have an emitter and a base.
Yeah, yep. But they're DC only also. They can't do an AC voltage. So, but this tech is the only one we deal with that has transistors. So that's why I wasn't going to go super far into it. And we don't usually use those to drive relays if we don't have to. We usually use them to drive valves and things like that. So then it doesn't matter. So, but yeah. Okay, so that was kind of my little spiel on the mechanical contact side of things. So the other downfall of them is it is a mechanical component, just like a contactor can fail in an air handler. Those relays can fail, right? It can burn up if you put too much current through it. It can chatter. It's just like any other relay. They're non-replaceable most of the time. So if you've got one that's doing a ton of on and off all day and it fries, a lot of controllers, we can move it to another output if we have to. That's if we have one available. But if you burn up a couple of them, you're replacing a controller. So they have their pluses and minuses. I've never personally seen a relay blow out on a controller because we don't really switch heavy loads. Usually, like I said, we're using a secondary isolation relay, and those things draw nothing. So it's pretty rare. The next kind we're going to talk about is a Triac. So a Triac is a solid state relay. They can only do AC loads, so no, damn it, I keep doing it, no DC. So you're only gonna get like 24 volts AC out of most of them. We don't really have any controllers that switch 110 or anything crazy like that. The one benefit of a Triac over a relay is the speed. They're instantaneous, like milliseconds, like way down there in their response time. So if you're doing something that's a really quick, you don't want any kind of dwell or anything like that when you command it, it's a Triac. They're fast. Because all it is opening up a silicon gate. I mean, it's not like an actual wait for the spring to compress and all that. It's way faster. Nothing we do matters in that because we're not doing like process control and stuff like that, but it is a benefit of them that I just wanted to touch on. As I was saying about the relay being better suited to heavier loads, most Triacs are limited at like 1 amp. They cannot hold a load because it's not an actual set of contacts. So it is, I'm trying to think how to explain a Triac. Think of it like what's the best way to explain a Triac? If you've got a box, like, and let's say all of your atoms are going this way. And this is a really dumbed down expression of how this works. But if you apply voltage in some fashion, because I don't know how it works, to this side, it literally will flip all of these atoms and charge them to where they turn the other direction and allow current to pass through. That's how it works. It's freaking voodoo. I don't get it. But the beauty of it is you don't really need to know how. It's cool to know it, but like that doesn't matter to us, right? We know that it's switching voltage some way, somehow. That's all that matters to us. The weird thing about Triacs, and I'll cover this more when we get into the troubleshooting side of it, a Triac will always show voltage unless it has a load. So if you take the wires off of a Triac and you put a meter across it, it's gonna show 24 volts, even with no command.
There's no way to like discharge it?
Nope. So if you take a relay though and put on there and then put your meter on the wires, it will not show voltage anymore because it has a load. So it's freaking, like I said earlier, voodoo, man. So I use a relay to test Triacs. I have a little 24 volt ice cube relay and I just wire it into my output and I turn the output on, turn the output off and see if that relay works. That's how I test them. It's the easiest way. So some meters will show wonky voltage when there's no load on them. Some will read them a little better than others, but the easiest way is just to put a load on it and verify. So, and I like I said, I keep a little, it's a $15 Varus relay with a little pigtail on it, and I'll unwire whatever the field load is, wire mine in there, drive that output, test it. I know it works because I know that relay works. I know the wire's good. So it's just a way to like limit out what could be the problem. So as I was saying, there is a third type, which is a transistor. Transistor is like a solid state relay, just like a Triac is, but it's DC only. There's a couple other little weird caveats about it, but we don't do them a whole lot. Like I said, we only have one line of controllers that use transistors for binary outputs. They are used in all the analog outputs. That's a given. Well, I guess they're not used in the milliamp style, but in 4 to 20 stuff. But any of our 0 to 10s, those are transistors. So it's just a different way of setting up that transistor to make it a binary. It's just an on or off style. Cool, yeah. There is the second thing about outputs we need to talk about is the other kind, the fun ones. The little transistor thing is a transition into modulating outputs. Do I? Huh?
Are you proud of that one?
Oh, the transistors to a transition? It was thought of on the spot. I didn't plan it out, if that's what you're getting at. Yeah, I really didn't. Look, transistors are second, not third in my sheet. I was on the run there. So just like inputs, where we have binary and modulating, we have binary and modulating outputs, right? Makes sense. Modulating is just like the inputs. It's going to be a scaled output. So basically, it's instead of being on or off, you have what could basically be an infinite value of range on that output. Infinite range of value. Damn it, I'm dyslexic. On that output. So 0 to 10s, 4 to 20s, those output values can be scaled for percentages, for pressure, for whatever, right? Like if you have a drive, right? Takes a 0 to 10, that drive converts the 0 to 10 to static pressure. It knows, hey, I need to ramp this drive up based on that output. So some examples are VFD commands, actuators, E to P transducers, electronic to pneumatic transducers. So if you've got a pneumatic valve actuator, but you have a DDC controller, you use a E to P transducer to convert that digital signal to a pneumatic signal. Yeah, so they are 0 to 10, anywhere in that range, or they are 4 to 20 milliamp. And you can take those outputs and scale them in any number of ways. Whatever you're sending that to is scaled. The third part of this, which is a little confusing, so y'all get how this works, right? Like, it's just a scaled output. It's either 0 to 10, 4 to 20, 2 to 10, 5 to 10, 0 to 5, whatever that scale you commit, your output is putting out can be scaled to whatever it is you're trying to control. Like if I need to control a VFD, that VFD is taking that 0 to 10 and converting it from 0 to 10 to 0 to 60 hertz, right? It knows that that's how that works. Your controller's programmed for that. Same thing with like valves. 0 would be closed or 100 would be closed, and then the other vice versa. So the weird one that really gives people fits is called, it's still a modulating output, but it's called floating control. So floating control uses two uses two binary outputs to drive an actuator. E to P, never seen a VFD with a floating control on it, but a lot of cheaper actuators, so like damper motors on VAV boxes, those little tiny cassette valves you find in like cassette ACs, like at schools and stuff like that, use them. So what floating does is you will have an open and a closed output. So like this may be DO1 and this may be DO2 on a controller, and then there'd be a common, which would also be a common. So your field device is gonna have 3 wires, common, open, closed. So to open a valve, DO1 is gonna fire for a predetermined amount of time based on the speed of this actuator. So like a common speed is 90 seconds equals 90 degrees on a damper actuator. So if I want to open that actuator to 50%, I'm gonna send it 24 volts for 45 seconds. And it's gonna equal 50%. Then this output will stop. And then if I wanna close it, I have to fire this output for 45 seconds, and it will drive it back the other way. So the reason these are such a pain in the butt is because you don't have a constant signal. People struggle to troubleshoot them because it's voltage over time. So the other problem is actuators are not always exactly 90 degrees for 90 seconds for 90 degrees. You may end up with 92 seconds to get to 90 degrees because of some binding or something like that. Well, this controller can't factor that in because you predetermine how long these outputs have to fire to open that. Because you open that actuator up, the documentation says, all right, 90-second actuator for 90 degrees, you plug that into this output. They get out of sync. So this may open for 45 seconds, but that may not equal 50%. It may open to 40%. Well, when it goes to close it, it's gonna try and overdrive it closed. And then the next time it goes to open, it may go to, let's say, 75 degrees. and then it says, oh, well, I want to close it to 30, and it tries to close it to 30, but it keeps going past 30 because it actually takes longer, and they get out of sync. And that really drives people up the wall because they can't figure out why this actuator is not where it's supposed to be. So a lot of controllers that have this function have what they call a sync feature, and the sync will either drive it all the way open, and usually they add like 10 or 20% to the time in their sync feature, and so like Honeywell, when you power up a controller, it will sync the damper actuator. It'll drive it all the way open, and then all the way closed, and then it'll hold it there, and then it'll release it, and it'll start maintaining. So if you power down a Honeywell VAV box and you turn it back on, that damper is going to open all the way up first, then it's going to go all the way closed, and then it's going to start to maintain. So people are like, well, why is this thing open all the way up when I turn it back on? That's why. It's just because these get out of sync, so you have to put in a sync protocol in your controller to make sure they don't get out of sync. So if you don't have a sync protocol, then they get out of whack and you have to manually sync them, which means you force it open multiple times and make sure it opens, and then you force it closed multiple times and make sure it closes. Try and get it back in its range. Really, the only way to test these is with a meter and a way to drive the output, and then you can time it and make sure it's actually doing the right amount of time for that actuator. So if you come to it and you've got an actuator that's acting weird or it's not synced, you can unwire this, put your meter across DO1 in common, run it to 100%, and then stopwatch it, see how long it runs for, and then confirm that against the literature on the controller, on the actuator, to make sure they match. There's not really a whole lot, because as long as it's putting out voltage, you know the output works. But then you got to confirm if the output is right for the actuator. It gets kind of retarded. Luckily, we don't see these a lot on valves. It's usually just on VAV boxes is the most common place for them. Most valves and stuff have the true 0 to 10 modulating stuff, so you don't really have to struggle with it too much.
So say if you have a whole building of VAVs.
I didn't ask for questions yet. Yeah.
Do you do like a daily sync or whatever?
Yes. So some do, some don't. Not all of them. It all depends on how it's set up. But Honeywell syncs on occupied. So, but you can change it. There's a check button in the logic for those actuators where I can change where it syncs when it comes occupied, and I can sync when it goes unoccupied. Now, some buildings we have to do like a 24-hour sync because they don't turn off, like hotels, hospitals, things like that. But you can program in a 24-hour sync. So there's a couple ways to do it. You can either do it in the sync logic itself inside of the controller, or you can, every 24 hours, blip the box for 5 minutes unoccupied. You don't have a schedule per se, but you send an off signal to the box. It syncs, then it fires right back up. So, all right. I'm gonna do a real quick, how to troubleshoot all the different inputs and outputs. I'm not gonna go super detailed unless y'all got questions, but so if you need to test a binary input on a controller, in my opinion, solely my opinion, this is my train of thought, the first thing I'm gonna do is confirm the actual field device, right? So if I'm looking at a, let's say I have an in switch on a damper, okay? And I go look at that damper, I know it's 100% open. I can put a meter on that in switch, make sure the contact's closed. I can go back to the controller, I unwire the wire for that input from the controller, I then check that wire, I make sure that wire has the contact as closed, so we know we don't have a cut wire. The next thing to do would be to jumper off that input, right, with something works. And then if it still doesn't go off, the input's probably bad or configured wrong at least. Basically, you're You confirm your field device, confirm your wiring, double verify the input's bad. And then I would write it up and say the input's bad. Problem is, once you get to that, it's usually either move the input, reprogram the controller, or replace the controller completely. It just depends on if you have the open I/O to move it. A lot of times we don't end up with enough I/O to be able to move it. We have to replace the controller. Modulating inputs, same basic thing. If you've got a temperature sensor, like I was saying earlier, if we have a thermistor with a well in a chill water pipe, right? You can take your, say you have a, like one of the mechanical little mercury sensors next to it, right? It says temperature's 54 degrees. You take the sensor, you unwire it, you put your meter on the leads, you check the resistance there, note it, look up the chart for that thermistor, see if those values match, right? Whatever your resistance is at 55 degrees on the chart is whatever that sensor is reading on your meter for ohms. If that's the case, you go back to the controller, or sorry, you wire it all back up, go back to the controller, check the wire, because they may have not scaled it or something for their own value in the wire, or it may be that somebody replaced the sensor and put in the wrong sensor for that input. Basically, you're never really checking the controller much on inputs. You're more checking your field devices. So you just need to know what you're looking for. The only way you would be able to test that input is, say, if you have a rheostat with a known value, right? Like, I used to carry this little rheostat that was around 10,000 ohms, and I could dial it in and then make sure that controller read the temperature that I thought it should read at 10,000 ohms based on how it was configured. That's really the only way you can test the input to see if the value the controller reads matches the field value. So
So you're saying just verify everything else first? And
Yeah.
Everything else.
if everything's right and you're still not getting the right answer on the controller, the only other thing that it can be, if it's not the input, is how the controller's configured, right? Like it's set up for the wrong sensor, or it's set up for a different sensor. You know, it may be that it's a Honeywell controller that's set up for a 20K sensor. Well, somebody had a spare 10K laying around, didn't know it was a 10K, and they just stuck it in there, and now it's reading all kinds of crazy. I actually had a job the other day that happened to. They replaced these well sensors in a central plant, and they were all of a sudden reading 94 degrees. They didn't know why. They put the wrong sensors in. So super simple, quick, easy fix, nothing to it. They just grabbed two sensors that were on the shelf. They didn't know. They were actually duct sensors. And the way that happened is their plant controllers use 10K sensors. Their duct sensors in all their boxes are 20K sensors. They didn't know that. They just grabbed this two spare sensors sitting on the shelf, plugged them into those thermo wells, thought they were good to go. They weren't. So, but as far as checking outputs, oh, hang on, we'll get to, yeah, we'll do outputs. Kind of went over like with the Triacs, putting a meter on them. You're gonna always show voltage if they don't have a load. If you have a load, like a little relay hooked up to them, then you'll be able to really tell if they're calling or not. So you fire that output, you should see 24 volts, you take it off, you should see something less than 24 volts. It's still gonna show some voltage just because it's solid state, right? It's never opening up a set of contacts and closing off. You may see like 3 volts, 5 volts, something around there. But as long as it's not at 24, it should be off. Like I said, my favorite way to test it is just with a little pigtail and a relay that I know works. Fire the output. If the relay clicks, I know it's good. As far as checking a modulating output, I kind of went over the floating style, how you got to know what your actuator's timed for. You're basically putting a meter on it and checking to see how long that output stays on, right? Because you may see that, oh, hey, this relay, if it's a relay style floating output, that relay may be failing, right? It may do 24 volts at first, but then after like 30, 40 seconds of driving, it may start to get weak. The coil may be going bad and it may drop out. It may not ever be able to run for 90 seconds. So, and then especially with a load on it, you know, if you took the load off, put your meter on it without the load on it, you may get the 24 volts for the full 90 seconds, but you put the actuator back on it and it gets a load. If that actuator is going bad and starting to draw more and the contact heats up, it may fail at that point. So it's the best way to check those is just wire them up, put a meter on them, and then time them out. Make sure they hold for the entire time they're supposed to. Make sure you don't lose voltage. Make sure you have a consistent voltage. You're not getting like a drop across it if the contact's failing. To test analog stuff, if you cannot drive that output and watch your field device move, like if the controller's in another room or something like that, then I'd just unwire the wires, put my meter on the output, see if it's driving to 10, see if it's driving to 0, 4 to 20, whatever it may be, and then go to your field device and use a signal generator or pull the wires off of the field device, see if you get your 10 volts there. If you've got 10 volts at the wire and the actuator's still not working, then it's probably a bad actuator, right? Like, because you know you've got voltage all the way up to the actuator. So the output's working because you've got voltage at the output and you've got voltage at the field device. Just now the field device isn't working. We don't really see a ton of failed outputs and inputs. Usually it's voltage takes a controller out or something to that nature before they ever fail. I mean, they life cycle those things a fair amount. I guess you can get like some factory flaws and stuff like that that'll kill them, but it's pretty rare that they actually just flat out fail. So usually it's something takes them out. You've got either a bad field device that caused that output to burn up or something like that. And usually when you end up with a bad field device or a bad output, there's a bad field device to go with it. So you usually end up replacing more than just one thing. But I'm trying to think if there's anything else we can touch on because I'm hungry. You understand what I was saying about the milliamps thing with testing it? How you put a meter in series? Yeah. So like if you've got, so this is our controller. It's got 2 terminals. You've got your wires coming in from the field. What you would do is, here's your little meter. You've got your leads, little screen. You would unwire this wire, put your meter to that wire and your meter to that terminal. And then you set your meter to amps, and then the current goes through the meter and it's able to read the amp draw that way. So like I said, not all meters can read milliamps. Actually, like I think the Fluke HVAC one may be one, but like there's only a couple of them that actually will read them reliably. So I know I've got this one little wonky one that reads them, but I can't find them anymore. So if I ever break it, I'm screwed. But
So, might be a dumb question, but as far as inputs, outputs go on your controller, if you're, I ran into something the other day.
oh, give me what you got. Yeah, no, we were talking about something the other day, testing that SCR heater.
Yeah,
Yep.
So, is there a way, because I know like you get comms wire coming from, I guess your front end, whatever's controlling into your controller, the BAS says it's calling for heat. Is there a way for me to confirm at the controller that I'm getting the correct command for heat to the controller?
To the controller?
Yeah.
To the controller or from the controller?
To. And I'll go just that controller.
Okay, so we'll do a real quick overview, control system wise. And we're gonna do a field device class next, all right? So I'm just gonna, we're here, let's just talk it over. So we have a computer, right, at the engineer's office. This is our PC, okay? This PC is networked over to what we call a Jace, okay? This is internet, right? These may be in 2 separate buildings. They may be right next to each other. They may be on different floors, whatever. This is an IP connection, okay? Out of the Jace, you also have typically what we use is BACnet, but there are multiple other protocols of MSTP, Master Slave Token Passing. Okay, so this is a hardwired connection between this device and your controller. Okay, and then out of there, you have another wire that will go to the next controller, and then another wire that will go to the next controller until you reach the last one. So these are all C's, right? These are all controllers. So this guy doesn't really do anything. This is just an interface with this guy, okay? So this is what allows you to pull up the graphics that are in here, the points that this is reading, so forth. This guy talks to all your field devices over the MSTP network and gets values from each of them and sends them commands and values. So then once it gets an occupancy command, a set point, this controller determines what it does with all those things, right? You've got ins and you've got outs. So it'll take a temperature and it knows, hey, and a set point, it will compare the two and then decide what to do with an output. Maybe it opens a damper, it fires a heater, whatever, okay? Most of these will work without that there. They don't need it. They will default to occupied and they will default to a set point. All the logic to control their stuff is in them. Not in here, not in here. So even if you were to completely wipe this out and do what we call a standalone system, where there's just a controller and a VAV box, they'll do their own thing. They have a temperature and a set point and they're set to occupied. So that's just a quick explanation. As long as this controller, I'm gonna draw it bigger now, is set up and getting, let's just say this is our temp, this is our set point, this is our damper, this is our heater, okay? This set point could come from a wall sensor with a dial on it or a slider. Temperature comes from the same sensor. As long as this controller, if it is standalone, set up to run all the time, or if it is networked and it's given a command to be occupied, it will compare these two and determine what these outputs do. If you're looking at a front end and you're getting updated values and it's saying this is putting out 100% heat, you should be able to come to these two terminals, put a meter on them, and get a value. I don't know what that value is supposed to be. It could be a 0 to 10, it could be an on-off, it can be 0 to 5, it could be whatever, but you'll get a value at those terminals. So if you're not getting a value here, either this controller is not calling for it, you've got the wrong output, or the output's bad. Or it could be miswired and it could be grounding that output out and you're not reading an output, even though it has one. That happened to me last Friday night. I would come to the controller, get an output. This controller then went over to another panel, which had some EPs in them. And then those EPs sent pneumatic out to a valve actuator. I would come in here and I'd measure here and I'd have nothing. So I'd unwire this, check that again, I'd have voltage, wire it back up, come over here, nothing. I'd unwire this, check it, I'd have it. Well, these guys were all sharing 24 volts. Somebody had taken out the third EP in this panel and left this wire just hanging in the panel and it grounded itself out. And it shorted all of it and nothing was working because of a wire that nobody disconnected. So I had it here I had it here, but if I would land this here, this was shorted internally to ground and I lost my signal.
Yeah, I wasn't getting anything out of the controller, but when I put 9 volts DC to the
SCR,
signal,
yep.
it came on.
Okay. So at that point, the only thing you can do, you would need to go in that controller, make sure you have the right output, first off, because they may have miswired it, right? Like, I mean, that's happened hundreds of times. Even with us, like, that's why we always double check our work. So,
Other outputs for the
well,
signal you want.
not necessarily. Honestly, the easiest thing to do would be to call one of us and just have us look at it real quick, because it's the fastest way to do it, right? Because for you to figure out which input it is high level stuff, right? Like, sometimes there's an easy way to figure out which output it is, sometimes there's not. To drill down in there and look in the program and figure out which output it is and how it's configured is something I couldn't walk you through over the phone, right? So, but it would take me 30, 45 seconds to do it myself. And we can do that remotely in most of our buildings. Some we can't, and in that case, I would sit on the phone and try and help you figure it out. But yes, in theory, you could test all the other outputs and look, but if the output's configured wrong, like it could have been, originally that box was a staged heat, and they replaced the box in a TI, but they didn't reprogram the controller. Happens all the time. And now you've got a controller that's putting out 24 volts for an output that's wired up to a SCR. It doesn't do anything. So it just, there's so many things that can go wrong that you need a little bit more information to know right. You know what I mean? And then a lot of times, I don't even necessarily have to look at the controller to tell you where it should be. Like Distech, it's always gonna be a particular output, right? Like Distech is, if you're a staged heat, it's outputs 1, 2, and 3. Output 4 is fan. Analog is always analogs 5 or 6. Every time. Unless someone has written a completely custom program, that's how it's gonna be. So 90% of the time, it's gonna be those outputs. So if you call me like, hey, I got a Distech controller on a fan power box, the wire's wired up to this, say the SCR is wired up to DO1, I'm gonna tell you that's wrong. It's wired up to the wrong DO. Check UO5, see if you have voltage there. If you don't, it's not configured properly. We need to change the configuration and move the wire over to UO5. So but like, I tell you that now, when are you gonna see that again and remember it, right? Like, I deal with that all day, every day. You might, and that's why I'm telling you. So, but I mean, even with us, like, we deal with this stuff every day, but you don't always, I don't deal with that controller every day or that controller every day. So like Kevin knows stuff I don't know. I know stuff Kevin doesn't know. We're always bouncing stuff off each other. That's why we're always answering the phone for y'all when y'all call us, because it's the easiest way to learn stuff, right? Just experience. All the different things that you come across, you just slowly build up that repertoire of knowledge. So, but yeah, I would hazard to guess it's either set up incorrectly or miswired. And I would venture to say it's probably miswired. But so you were just putting your meter on where you took the wires off, right? Or did you have the wires still landed? I had the wires still landed. Okay, that's how I would do it too. I wouldn't take them off. But did you check for voltage at the field device? Like, so if, the controller is wired up to, 2 wires come out and they go over to the SCR, did you take these 2 off and test across them to see if you had anything?
No, I tested across the post where it landed
Yeah,
on the board.
see, I would take them off because this may be screwed up somewhere or something, and it may be grounding out like I had the other night.
I put 10 volts to
I get that, but that is a separate 10 volts, not something coming from the same panel. So there may be something somewhere else. It's not even involved with this SCR, right? Because all this SCR needs is that 0 to 10 to drive. It's got 24 volts powering it, and then it has a 0 to 10 input. this 0 to 10 input can be sourced from a completely different source, and you may not have that problem. Whereas this, let me clean this up a little. So let's say this is our 24 volts, right? Coming from the controller. That's coming from a transformer over here. Okay, so this transformer powers the controller, and then it may be jumpered from up here, it may be coming straight from the controller. That feeds power to here. Then out of our controller, we have our 0 to 10. Well, there may be something causing this common to get wigged out that's making you not get that 10 volts through these wires. But if you take a separate signal generator and wire up over here and take all this out, you've removed the short and it works. So, you know, your short's still back here, not at the physical device, it's somewhere else in the panel. And that may be what's causing your problem. So that's why I always like to take these off, make sure I have my signal there, make sure I have my signal at the controller. I mean, it could be as simple as these two wires could be touching inside the jacket. Somebody could have pinched them and they could be touching. So you take it here before that short and it reads voltage. You come after the short and it doesn't. So it just depends. There's so many variables and stuff. It's just variable, you know, just completely variable. But like I said, we'll get deep into field device troubleshooting on the next one. This was just inputs and outputs. So we'll actually use some teaching aids. So, but we'll see. We'll play it by ear. Maybe break some shit, you know, whatever. So maybe not like that one time we did actuators.
I was gonna say, last time we did actuators.
Yeah, I know. Yeah, springs bouncing across the building. No, we'll keep it a little less than that, but we'll bring some field devices and just show like how they wire up, how to make sure they're wired up right, talk about them, talk about it, you know, the physical constraints of it and how they need to be wired, and like not taking two transformers to do one job and all that kind of fun stuff. So that's it for today. Everybody have a good night.